Today, we're going to continue talking about sequences, series, and power series. If you would recall, we've been in the middle of trying to determine whether a given series converges or diverges. So that is, we're looking at a sum with an infinite number of terms, and we want to figure out how we can tell if that infinite number of terms produces a finite sum or an infinite sum. The big thing that we have is our necessary but not sufficient condition. If the limit of the terms is not zero, then the series diverges. This is logically equivalent to the contrapositive. If a series converges, then the limit of the terms must be zero. But this is not a sufficient condition for convergence. Yesterday, we saw that the harmonic series diverges even though the limit of the terms is equal to zero. But this is a great place to start. If we can see that the terms don't go to zero, we're done. The series diverges. I've been saying that so I want to make another distinction. When I say a series converges means the sum is finite, doesn't mean if we negate that if a series diverges, then the sum is infinite. What we mean is that there's no sum that we can determine. That's what that means. So we got to be careful about how we negate statements. So not finite, when we think about sums, we sometimes automatically go to, well, it must be infinite. If it's not finite, it must be infinite. But it might be that we cannot determine a value. Like the y division by zero is undefined. It's not infinity, it's not negative infinity, it is indeterminate. So what I mean is, so note, if a series diverges, it doesn't mean the sum is infinity. Oops. Let's just phrase it this way. The series diverges is not the same as the sum is infinite. It might just be that we cannot determine what the sum is. For example, the series as n goes from 0 to infinity of -1 to the n. This is a divergent series. Limit of the terms is not 0. When we look at the series, we have 1, and then when we plug in n equals 1, we get -1, +1, -1, +1, -1, +1, -1, plus, and so on. This series does not have a sum. We can't say it's infinite. We can't say it's finite. The series diverges. If we look at the limit of the terms, the limit as n goes to infinity of -1 to the n does not exist. Therefore, the series diverges. Now, it might be that you want to look at this and say the sum should be 0, because we have 1 - 1 plus 1 - 1 plus 1 - 1 plus 1 - 1. And so that's just all zeros. But we don't get to do that. We don't just get to associate. We don't just get to group these up how we want, because we're not dealing with addition. We're dealing with, we can't apply the rules of addition because this sum is not associative. We don't have a plus b plus c. We have an infinite number of terms. And that does not apply in this case. There are too many things going on. We can't just do the associative property. So we can't just read this as 1 - 1 plus 1 minus 1 plus 1 minus 1 plus, and so on. If we can do the associative property, if we allow ourselves to do the associative property, then there's nothing to stop us from saying this is 1 plus negative 1 plus 1 plus negative 1 plus 1 plus negative 1 plus 1, and so on. And now our sum is 1. We can't determine which one it is, so it can't be either. So we don't get to use the associative property when we have a divergent series. That's the problem. This is the thing that we don't understand about infinity that we're trying to understand about infinity in this class. And that's why calculus is about infinity. We don't get to use the associative property. We do not get to use the regular rules of addition, associative property, commutative property, on a divergent series. Sometimes this is presented as an argument that 0 is equal to 1. If your conclusion is that 0 is equal to 1, then your argument on its face is faulty. That's just a fact. 0 is not equal to 1. If your conclusion requires that 0 equals to 1, your premise is super flawed, which is actually a great way to make an argument in math. You assume something to be true, and if you can show that that assumption leads to a contradiction, like 0 equals 1, then you can go back to your original principle and say the original principle, the original assumption must be false. Because if it is true, then 0 is equal to 1. So clearly, we cannot use the regular rules for addition on a divergent series. If we could, then 0 is equal to 1. Since 0 is not equal to 1, we cannot use the regular rules for addition on a divergent series. All right, so that's the big thing. That's our necessary but not sufficient condition. Then we had a next big thing, which was the integral test. Where we had a series that we're trying to determine converges or diverges. And we just turn it into a function. Now, the convergence of the series rests on the convergence of the improper integral. So we could say, if the improper integral from 1 to infinity of f of x to x converges, then the series converges. Similarly, diverges. This is useful because it gives us something to calculate. If we can find the antiderivative of f of x, then we have a tool that we can use to determine the convergence of a series. One thing to note here is that the default is to start the integral at 1, but the convergence and divergence happens at infinity. So we don't have to start at 1. The 1 can actually be any value. So if the function, for example, is say 1 over x minus 1, we can't plug in 1, so start at 2. So we can start anywhere. It's the infinity side that we're interested in. We can really start anywhere. If there's going to be a problem, infinity is going to cause it. If there's going to be a problem, it's going to be with the infinity, not the 1. If you're setting up an improper integral and someone comes along, it's like, oh, but look, you started off at 1, but the function is undefined at 5. What are you going to do now? Start at 6? That person is not making a valid argument. Or they just don't understand what you're doing, which is, at this point in your mathematical career, more likely. Someone's just not going to understand what you're doing. You know what I mean? If they should know better, then they're either trying to test you because they're your teacher, or they're arguing in bad faith, in which case just ignore them. It's part of the critical thinking thing. Know that when someone comes with you with certain arguments, you have to identify that they're arguing in bad faith and they should be ignored. They should be called out on that and then ignored. And just be told, that's cute. Come back when you have an actual argument. You know what I mean? So here's the important thing that we get from the integral test. So remember, in the integral test, we're finding an antiderivative. So we are adding 1 to the exponent and then dividing by the new exponent. So an important result of the integral test is what we can call a p-series. And where we can say the series 1 over n raised to the p power converges if p is strictly greater than 1. If p is strictly greater than 1, then when we add 1 to the exponent, the n is still in the denominator. And so when n goes to infinity, that term goes to 0. So the series 1 over n to the p converges if p is greater than 1 and diverges otherwise. So what we want to remember from this is a result of the integral test, because when we add 1 to the exponents, if p is greater than 1, the n is still in the denominator. So if p is greater than 1, the antiderivative has n in the denominator. So when n goes to infinity, that term goes to 0. And the p-series diverges if p is less than or equal to 1, because the antiderivative will have an n in the numerator. If p is less than 1, then when we add 1 to the exponent, the n will end up in the numerator. So in this case, the antiderivative has an n in the numerator. So when n goes to infinity, the n to the negative p plus 1 goes to infinity as well. Or we end up with a natural log. And the natural log still goes to infinity as n goes to infinity. So this is just going back to our antiderivative rules. The integral of x to the n dx is x to the n plus 1. We add 1 to the exponent and divide by the new exponent. So an important result of the integral test is that we get these p series. An important thing to notice at this point is, say, this is a very limited scope, very limited number of type of series to have. Not everything looks like 1 over n to the p. What if there's a bunch of other stuff going on? So this seems very limited. What if there's more stuff going on in our term? Thankfully, we have the comparison tests. So we're going to set up two ways that we can use these p series, these very simple series that it's easy to determine if they converge or diverge. And we're going to use the comparison tests to do it. So an important thing to note about the comparison tests, we don't pull the comparison test off the tool shelf because we don't know what's going to happen. For the comparison test to work, both of them, for either comparison test to work, we pretty much have to know if the series converges or diverges. Otherwise, we won't know which version of the comparison test to use. So it's not a test in the regards where we say, let's find out if the series converges. To use a comparison test, you pretty much already have to know that the series converges. Otherwise, you'll be making the wrong comparison. So let's talk about how the comparison tests work. Let's first just state what they are and then use the power of reading to see how they'll be useful. So the first is the comparison test. We're going to be making a comparison, so we don't need one, we need two series. So the comparison test says let AN and BN be series. One of these series is the given series that we're trying to determine. The other one is a known convergent or a known divergent series. So one of these is the given series. The other one is a known series, something that we already know converges or diverges. In the comparison test, we're going to have a bigger series and a smaller series. So let AN and BN be series. And let's squeeze AN between 0 and BN. This doesn't have to be for all n, it just has to be for all n after a certain value of n. Eventually, we have to be able to squeeze AN under BN. It doesn't matter if for n equals 1 to 100, AN is bigger than BN, so long as after 100, AN will always be less than BN. So it does require that everything be positive for this to work out. We have to be able to squeeze AN between 0 and BN. So if the series AN diverges, then the series BN diverges as well. That makes sense. If we have something that's being squeezed between Bn and 0, if I add up all the An and that goes to infinity, and all the Bn are bigger than that, then the series Bn will also have to go to infinity. So if the series So we get two conclusions. If the series AN diverges, then the series BN diverges as well. In the other direction, if the bigger series converges, then the smaller series converges as well. You're not going to be able to hide an infinity underneath a finite. So if the series Bn converges, then the series AN converges as well. If the series AN, if the smaller one converges, then we get nothing. And if the bigger one diverges, then we get nothing. But we have a smaller series and a larger series. If the smaller series diverges, then the larger series diverges. If the larger series converges, then the smaller series converges. Those are the two things that we get out of the comparison test. I was looking at these, I matched the orange with the blue, and all of a sudden I felt like I was using Mets colors, but it's kind of more Miami Dolphins colors because the blue is a little bit light. But like the Mets colors. Oh yeah, that's good. This is I'm using Gulf livery for the comparison test, so that works even better. Because yeah, the Mets. The Mets are what happened when when the biggest rivalry in baseball left New York, and so New York got all sad because they weren't the biggest. That's why there's a rivalry between New York Yankees and the Red Sox. I mean, there's the Babe Ruth thing, but the big deal in baseball at the time was Giants Dodgers. But when the Giants and the Dodgers left town, New York was no longer the center of this big rivalry, so they felt bad because New York has to be the center of everything. So, like the big babies they are, they created the Mets. And that's why the Mets colors are blue and orange. Blue for the Dodgers and orange for the Giants. So, the Mets will always be a derivative team. I know in the 90s they started wearing the black uniforms, but then all the teams started wearing black uniforms. So they're still mad about the Giants and the Dodgers leaving town. You know what I'm talking about? Anyway, I don't know if things are like that anymore. I don't know if anybody really cares. Eventually started looking at all these sports rivalries, and it's all fun and games until it's no longer fun and games. And then when it's no longer just fun and games, it's kind of pathetic. When people are getting into actual fist fights over which sports team is best, then it's just kind of sad, and I'm embarrassed for our species. Let's talk about the limit comparison test before I just get distracted even more by baseball. Once again, we need two series. Let AN and BN be series. So once again, one of these series is the given series that's in question. The other series is something that we know converges or diverges. So in the comparison tests, we're making a comparison. We're comparing. We're going to compare the given series to a series that we know. This is going to be especially useful because we just talked about the p-series, and now we know p-series really well. It's really easy to determine if a p-series converges. So those are going to be the ones that we pick for our known series. But we have a given series and a known series. So the limit comparison test has the following. Let AN and BN be series. And the limit comparison test has us calculate a limit. Not surprising because it's the limit comparison test. If the limit as n goes to infinity of the ratio of the terms of these series, if the limit as n goes to infinity of an over bn is equal to a non-zero constant, then both series converge or both series diverge. So if the limit as n goes to infinity of an over bn is some non-zero constant, then either both series converge or both series diverge. The important part is that we look at the limit at infinity of the ratio of the terms and come up with a non-zero constant. What the limit comparison test does is quantify what we mean when we say that one series behaves like another series. If the limit at infinity of this ratio is equal to 0, that means bn is substantially larger than an. And so the two series are not going to be behaving in the same way. If the limit as n goes to infinity of an over bn goes to infinity, that means an is substantially larger and the series are not behaving in the same way. But if in the long run, we get a non-zero constant, one is just a multiple of the other. And so either they both converge or both diverge because they're both behaving the same way. So this is how we can quantify one series behaves like another. And that's why our conclusion, if one series behaves like another, then they'll both do the same thing. They'll both converge or both diverge. And that's really what we're getting after in both of these comparison tests. In the direct comparison test, we have to have this direct comparison. There has to be a smaller one and a larger one. And so we want to see either the smaller one blowing up the larger one or the larger one containing the smaller one. But really what's going on is that we're trying to get one to behave like the other. The reason that we want the limit comparison test is that the limit comparison test is much better for making observations. It's easier just to look at things and say, oh yeah, that's going to behave like 1 over n to the third, and 1 over n to the third converges. So the limit comparison test is where we take a series. I'm out of space and I don't want to start a whole new page because there's like a minute left. So when we look at a series, let's say we have a series of 7 plus 2n plus n squared. And on the bottom, we have a 13 minus 100 n squared plus 6 n to the fourth. When we look at this series, when n is very large, In the numerator, the only thing that matters is the n squared. When n is a billion, we don't care about 7. If we buy a lottery ticket for $7 and we get $1 billion squared dollars, we really don't care about the 7 that we spent on the ticket. The only number, for large values of n, the only term that matters on top is the n squared. In the denominator, the only term that matters is 6n to the 4th. This minus 100n squared is nothing compared to an n to the 4th. A billion squared is what, 10 to the 18th? A billion to the 4th is 10 to the 2 times 18. I can't do arithmetic. I don't know if that's a more coffee problem or a less coffee problem. But I just know what solution I'm going to apply. So when we look at this rational function, the only thing that matters on top is n squared. The only thing that matters on the bottom is n to the 4th. So in our mind, we're thinking, well, there's an n squared on top and a 6 n to the 4th on the bottom. And so this is going to look like 1 over 6 n to the 4th. Sorry, n squared. Because of 2 of the factors of a billion will cancel out with 2 factors of the billion, but we'll still have 2 factors of a billion left over. And 1 over 6n squared will behave like 1 over n squared, so we can say that this converges. And this is all just taking place in our minds. And all we're doing is looking at the important terms. So this comparison test is really effective on rational functions. We could make this more rigorous, like when we're calculating limits in rational functions, but this is how we calculate limits in rational functions. And just look at the important terms. Think about what happens when n is very large. When n is a billion, n squared is what's important, not 2 billion or 7. When n is a billion, n to the 4th is what matters, not the n squared or the 13. All right, so homework for chapter 9 has been uploaded or published. It's ready to go. The rules should be in place where you can do as many attempts as you want. I say should be because I'm the one that set the rules, and I did this by a computer, and so who knows what's going to happen. So you should have unlimited number of attempts to do that, and you have a couple of weeks. I think I set the initial due date to be April 23rd. After April 23rd, there'll be a month left in class, and so we'll have to start doing final exam type stuff. Since we're not going to have 1 2.5-hour final exam, we're just going to have 1 month-long final exam, where you're just constantly doing problems. I'm just kidding. It's not like that. I just want to make sure you have a sufficient number of time to complete the problems. So I want to get them out there earlier rather than later. I know we should have had a traditional exam where we all have to log on at the same time. And then everybody has to have their camera on. And then I have to watch you carefully to make sure that you're not looking around or there's nobody else. But that's ridiculous. That's just ridiculous. There are certain things that we're just not going to be able to simulate. And I'm not even sure that we should be anyway. I'm not even sure that this is how we should be doing tests and final exams in the first place, where we all sit in a room and do the same set of problems. And I have to sit there and watch you to make sure that you're not cheating. I guess I just prefer to treat you like adults. You know, it's funny. One of the things that we had conversations about this, where this is how ridiculous conversations get between teachers. So one of the conversations was that should a teacher be allowed to flunk a student for cheating on a test, like flunk the whole class? Should you essentially be allowed to kick a student out for cheating? And the consensus was this weird half measure. It's like, well, you can't flunk them for the whole class, which makes sense to me. I think I think that when you cheat on an exam, when you try to defraud your instructor, I find that offensive. Like when it's an affront that is personally insulting to me. When the style of cheating is like, oh, Leach is so stupid he'll never notice. I always notice. But then you get like, the problem is you'll end up with these rabid teachers that are like, oh, I saw you peek to the left during the test, so you have to flunk the class. And that's just too far, in my opinion. So we were having these discussions about essentially, should you be allowed to essentially kick a student out of a class and make them take the entire class over again, just because they've done something that you determined is disingenuous. And the conclusion we came to was like, oh, no, you can flunk them on that thing that they were found to be cheating on, but you can't flunk them for the whole class. And so the devious part of my mind is, okay, you've said that I can flunk them on this thing. So if they're taking a test, I find that they're cheating, I'm allowed to flunk them. But this is still essentially not answering the question, because they don't say what the rules are for my grading they don't establish any kind of rules, and it's completely out of context for what the grading rules are. If there are 2 tests and your grade is based on those 2 tests, first of all, that's very bad course design. But flunking one of those things could cause you to flunk the entire class. So even though you're technically not flunking them for cheating on that one test, they did flunk because they flunked that one test, and they should just, you're essentially kicking them out of the class. Unless there are two tests, and flunking the test is defined to be half the points, in which case you can flunk the first one, ace the second one, and come up with a 75% and still pass. Now, it could be that there are 10 tests, each worth 10 points, and flunking one would just result in minus 10 points or minus 5 points. The point is, flunking is not a well-defined term. What if I'm allowed to flunk? I'm allowed to flunk you, but there's no prescription of how that is. So if you're caught cheating on a test, you flunk the test, and the penalty is minus 20 points. So if there are 10 tests, each worth 10 points, you flunk one, you don't get a 0 on that test. What if you get a negative 20? Your maximum score is 70, so you can still theoretically pass. But the problem is, we're working with a bunch of poorly defined terms, and math teachers especially should know better. Also, we're starting to see why the law is such a faulty mechanism. It's just that's just it. Because the language means different things to different people. So when people are like, oh, well, we should be able to flunk them on something. And really what it is teachers are insulted by a student trying to cheat on a test. The teacher gets insulted, and so they want to exact some kind of revenge. And to that, I'm just pretty much like, we got to grow up. You got to not take things personally. There are probably some students in this class that are not doing their own work. I see it happen. I wouldn't be able to prove it in court. But when you copy and paste someone else's work, it's really obvious. You need to know that. One of the reasons that you need to know that is that later on, when you come and ask me for a letter of recommendation, if you did that, I probably noticed, and that's probably the reason that I'm going to say no. I wouldn't say no outright. I would just say something like, are you really sure that you want me to be writing that letter for you? You know what I mean? So I'm saying that teachers need to grow up. I think also, especially college students, you need to grow up. It's one thing for those kind of shenanigans in high school. And I realize that the reason that students commit these kind of shenanigans is because of the way we treat them, because of the horrible way we treat our children by making them do things like take tests. Anyway, that was a lot of overtime nonsense about cheating and things like that. But I don't know. I think you guys need to hear these kinds of views because I think you've all been poisoned with the idea that everything has to be tests. And I'm worried that some of you might become teachers in the future and you're going to try to exact revenge on your students because you're going to be offended when the students try to cheat. When the real answer, which takes much more work, is going to try to create a culture where students don't feel that they need to cheat. Students should be confident to get things wrong, that they're going to be allowed to fix their mistakes. And that's the direction we should go, not try to come up with some, address the root cause is what I'm saying. And the root cause is that tests are stupid. They test how good you are at taking tests. And this is coming from a dude that's really good at taking written tests. When I'm taking written tests, I don't need to study. That's not a brag. That's just pointing at something stupid about me. I happen to be good at school. Since I haven't been a student in school for a long time, it's not exactly been a useful skill. And also, it doesn't make me a good learner. Being good at school has actually had the opposite effect. I am a terrible learner. Because I had some kind of natural facility for just kind of like coping with school. When I try to learn something on my own, I straight up cannot do it. You put me in a class and I'll be fine. It took me a long time to figure out how to do that, but you put me in a class and I'll be fine. But you say, hey, go teach yourself this thing, it's just not going to work. As evidence, I will put up my guitar playing. I've never been in a guitar playing class, so my guitar playing is utter trash because I've been teaching myself. There's no school that's forcing me to, keep up some kind of regimen. You know what I mean? And this is because I've been poisoned with the just pass the test and we'll all think you're smart. It's like, oh, just a test? That's it? You know what I mean? Anyway, we're way over time. That's it for today. That's it for this week. Everybody have a great weekend. I will take that advice, try to find a drummer to jam with, a drummer that can put up with my crap playing and find a drummer to jam with. Everybody have a good weekend. Start the chapter 9 homework so we can start answering questions on it. I will see y'all on Monday. Thanks for playing.